SwayamPrabha. Digital India. Educated India.
Welcome to the third lecture. We will continue with the applications. AAW, the Active Aeroelastic Wing program, it was led by Boeing Phantom Works and was supported by AFRL and NASA Dryden. It was about integration of wing flexibility, a distributed control actuation system and aeroelastic coupling. Here the goal was to enhance maneuver performance and minimize induced drag by controlling the lift distribution of a lightweight flexible wing. Induced drag is also known as lift induced drag, and it can be controlled by controlling the lift distribution, and that is what they did. Simultaneously, control of camber and the twist of high aspect ratio wing was also the goal. Enable is evaluation of new actuators in buffet load environment. It was initiated by US Air Force and other participants were from Boeing, NASA, Australia and Canada. Its goal was to address a very relevant problem, very practical problem that is encountered by high performance aircrafts. So, these high performance aircraft, when they are at high angle attack, they often experience something called buffet loads. Those are unsteady differential pressure, and that happens due to edge vortices, and it leads to premature fatigue of the airframe. And sometimes these vortices, they couple with other vortices that come from engine inlets and airframes, and that can be even more significant. See, here the goal was to examine the performance of two sheet actuators, and they are macro fiber composite actuator and active fiber composite actuator. So, these are composite actuators. So, here direction dependent actuation is possible. Macro fiber composite was invented by NASA. It is a piezoelectric composite, and it was then commercialized by Smart Materials in Germany. And during the wind tunnel test, they observed that power spectral density fluctuations for tip acceleration due to wing buffeting were reduced by almost 85%. Acrobat, that stands for Actively Controlled Response of Buffet Affected Tail. It was a NASA sponsored program and executed by Wright Laboratory and Daimler Chrysler. It used a 1/6 model of FA-18 wing with piezoelectric sheet actuators that was placed at an angle at its root. So, it was placed at an angle to ensure both bending and torsional deflection. A twin tail aircraft model was successfully tested in a low speed wind tunnel under the active vertical tail program led by McDonnell Douglas Aerospace to actively reduce buffet loads in a 5% scale by controlling the first two bending and first torsion modes using piezoelectric actuators attached to a spar. Then NASA had a morphing wing program that was initiated in 1990. Here the goal was to design vehicles to efficiently adapt to diverse mission scenarios through the use of smart materials, nanotechnology, adaptive structures, microflow control, biomimetic devices, structural optimization, controls and electronics. Now, we will talk about noise control in aircraft. So, noise is something where lot of research goes on. So, noise control is an issue. Noise comes from engine, turbulent boundary layer, air conditioning and so on. Now, most of the noise control methods are passive, and those passive techniques has been quite successful. Noise has been reduced by a satisfactory amount, and there are two items where a lot of research is going on. One is called acoustic metamaterials and sonic crystals. So, these are based on the metamaterials concepts, where a lot of research has been done and has been found to be quite useful. But the idea is that if some kind of active component is added to the solutions, then the efficiency can be further improved, and that is what has been done by in these two papers we can see. So, Gantry and others, they developed smart foam that uses polyurethane foam and PVDF actuators with a controller. Kim and Lee, they developed piezoelectric smart panels featuring piezoelectric shunt damping and passive sound absorbing material. Now, we will talk about jet engines. In jet engines, the problem is that if the jet engine has a fixed geometry inlet, then it does not it does not work optimally in a wide range of wind speed, because at different wind speed the requirement is different. For example, in the takeoff condition, large inlets with very blunt lips are needed. This ensures high inflow without flow separation. In the subsonic cruise condition, sharp inlet lips are desired to reduce the drag, whereas in supersonic condition the requirement kind of changes. The flow speed needs to be reduced to subsonic condition in the inlet. So, the solution lies in some kind of adaptive inlet geometry, which can adapt to the changing wind speed. Turner and others performed fabrication, benchtop testing and numerical validation of an adaptive jet engine chevron, which has shape memory alloy actuators embedded in a composite laminate. Now, composite laminates can be made shape adaptive just by orienting the plies in a sequencing the ply orientation in a proper way. So, we will talk about it when we discuss composite materials in more details. Now, again if some active component is added to it, here it has been done with the help of shape memory alloy actuators, it can be even more shape adaptive. Boeing 777-300ER with 11B engine, which has a variable geometry chevron, which it has 60 nitinol strip actuators. Now, Hartle and others, they carried out training and thermomechanical characterization of nitinol for application in the Boeing variable geometry chevron. So, after 50 thermomechanical cycles, the response was found to be quite stable with repeatable strain up to 1.6% over a wide range of applied stresses. So, shape memory alloys, they need something called training, where loading and unloading is done in a cyclic manner. We will talk about it again when we discuss shape memory alloy in more details. So, that is what was done here, and the observations are mentioned. More details can be found here. Samsung program has kind of similar goal. It is smart aircraft and marine propulsion system demonstration. It was between 1997 to 2000. The problem they addressed is similar, the limitation of fixed geometry inlet, which is not ideal for all flight conditions, and the engine's inlet has a direct impact on vehicles flight performance, mission effectiveness and life cycle cost. So, the goal here was to explore concepts for shape control using smart structures technology for gas turbine engine inlets for a typical aircraft and a large marine propulsion and hydrodynamic maneuvering system as well. In rotary wings aircraft, so for example, helicopter has a rotor. So, this rotor adds to significant complexity. First of all, a rotor has complex motion. Now, a rotor can have edge wise vibration, it can have flap wise vibration, it can have twist, and again there are several modes where all these motions are coupled. It is connected to a hub. The hub itself has its own complicated kinematics. So, that makes the vibration of the rotors quite complicated, and it is in complex aerodynamic environment. So, there are significant complexities that come: severe vibration and fatigue loads, aeroelastic instability, excessive noise, weak aerodynamic performance, and restricted flight envelope. And as mentioned, the primary source for all these problems are the rotor. So, three types of smart rotor concepts was developed: leading and trailing edge flaps actuated with smart material actuator, controllable camber twist blades with embedded piezoelectric elements fibers, active blade tips actuated with tailored smart structures. Now, we will talk about civil structures. The applications are diverse in civil engineering structures as well: structural health monitoring, vibration monitoring and suppression, minimization of vibratory loads, earthquake mitigation. The objective here is to maximize civil structure performance, to control structural motion, monitor health, minimize life cycle cost, and most importantly increase the overall safety. Now, major problem in structural health monitoring is internal damage. Civil structures deteriorate with time due to several factors: aging, overstress, fatigue, excessive use, inadequate inspection and maintenance, unexpected weather related problems. So, embedded distributed smart materials sensors to monitor the structural health is a solution. In the past, there has been several structural failures. Here is one example taken from the book: the collapse of Silver Bridge in Point Pleasant, that was in West Virginia, USA in 1967, and that resulted in loss of 46 lives. So, NBI National Bridge Inventory was formed to collect and store database of about 5,90,000 bridges. There is a study by Tennyson and others. They used fiber optic sensors for structural health monitoring. Now, so they with the fiber optic sensors, they monitor the strain at various parts of the bridge and as the vehicles passed by it, and strain variation like this was found. Now, with this kind of strain variation, if it is monitored on a regular basis, then any anomaly can be detected. That was the goal of this kind of works, and strain monitoring is used a lot with the help of fiber optic sensors for civil engineering structures. Suspension bridges and cable stayed bridges, they all have these cables as a major component of the structure. Now, apart from the loads due to the traffic or the earthquake load, wind load also causes a lot of severity in these structures. So, because of complicated interaction between the wind and the structure, phenomena like vortex induced vibration, flutter, they happen. An example is the failure of the Tacoma Narrows Bridge in USA. Now, it was observed that if the tension in the cable can be monitored, that can help a lot for monitoring of these bridges. So, that was the goal of this study carried out by Wang and others. So, they measured the tension in the cable using PVDF, piezoelectric film sensors. So, as was mentioned while comparing different smart materials, it was seen that PVDF has much low elastic modulus as compared to PZT. Now, because these cables are somewhat flexible, so PVDF was found to be a better solution here. and it was observed that the frequency analysis of measured cable tension with PVDF films and comparison with accelerometer data demonstrated the robustness of these sensors, especially in the case of cable sagging. Now, vibration control is also another aspect. So, magnetorheological fluid is quite a lot used for this kind of applications. Semi-active MR damper is used to stabilize large amplitude motions due to high gusty winds and traffic vehicles. It helps in reduction of fatigue and corrosion of the strands and increase the safety and durability of the bridges. So, Gordani Nezard, they used MR dampers in a 1/12 scale bridge model using a combination of passive and active damping to control the vibration of two span. So, MR dampers are finding growing applications in this civil engineering structures. So, a extensive study on MR damper for seismic and wind excited buildings can be found here, and here we can find some optimization also for proper usage of these dampers. Now, we will spend some time on structural health monitoring, because it is a very cross disciplinary problem. Aerospace structures, civil structures, mechanical structures, marine structures, everywhere the monitoring of the health is needed to enhance safety and efficient use of these structures. Structural health monitoring is basically based on the principle of looking at the structural response to some known or unknown excitation, and from the response data is analyzed and some information about the structural health is assessed. So, it can be structural health monitoring can be passive. So, in a passive, generally no actuator is needed. So, whatever the structural data is obtained from the because of the ambient condition, that is used to find out the structural damage status. So, examples can be in passive examples can be vibration based monitoring. Now, vibration based monitoring can be done with known vibration also by hitting it with a impact hammer or shaker, but when the vibration based monitoring is done just by looking at the ambient vibration due to the ambient load condition, that is a passive monitoring. Acoustic emission, these are all passive techniques. Active techniques involved actuation. So, some known signal is given to the structure and the structural response is looked into. So, it can be a guided wave based technique, electromechanical impedance, technique. These are all active health monitoring techniques. So, in an electromechanical impedance based technique, if I have a structure, then if I have some piezoelectric patch fitted to it, if I apply some voltage to it, I can measure the current also across this patch. So, the V by I, this ratio is the electromechanical impedance electromechanical impedance obtained here. It is electromechanical because this impedance depends on the structural property also. If there is some flaw in the structure, this impedance changes, and from this change structural health can be assessed. Now, here is one example here. Here an experiment is being done in our lab to find out any looseness in bolts. So, it needs a impedance analyzer and it has bolts, the looseness of which is being monitored, and it has piezoelectric patches. Guided wave based monitoring. So, in guided wave based monitoring, guided waves are waves that travel by, I mean that's traveling of which is guided by some wave guides. So, one of the example is lab wave, where the wave guide is the two opposite surfaces of a thin structure like a thin plate, as can be seen here. So, the wave remains confined within this thin boundary and travels. So, these waves can travel a long distance. So, that is why they are quite useful, because with small number of actuators a larger area can be scanned. Now, a very simple schematic view of a guided wave based system can be like this. So, if I have a piezoelectric patch here, if I excite it here, the wave propagates and the wave is sensed here. Now, during propagation, if it encounters any damage, the sensing response that we get here changes, and from that change again we can find out if there is any problem in the structure or not. So, here is one experiment, guided wave based experiment shown here. So, we can see a plate, here is a piezoelectric actuator which is excited by a function generator, and there is a sensor, the data is collected through an oscilloscope, and it tries to find out any problem in the structure along this dimension. So, this video shows the propagation of guided wave. The guided wave is generated by a piezoelectric patch which is placed at the center. Now, because this structure is isotropic and the piezoelectric patch that we used was circular here. So, the wave is propagating uniformly across all the directions, and we will see how damage is changing the propagation pattern. So, once the wave is reaching here, we have put some damage here. We can see that because of this damage the wave is getting scattered. So, the wave propagation pattern here is somewhat different from the wave propagation pattern here. So, any sensor that is placed here, the reading that it gets will be different from any sensor that is placed here where there is no damage. So, the wave propagation pattern also incorporates information about damage, and the goal is to extract the damage information from the wave propagation pattern. Now, it has several complexities. For example, when the wave hits the edges, again it comes back. So, there are lots of reflections. So, it needs lots of advanced processing to find out the damage from this wave propagation. So, that was just to give an idea about the application of these piezoelectric materials for damage detection using guided waves. In automotive system also, smart materials find lot of use. It is generally in active control of vibration, active suspension and engine mount, fluid injectors for diesel and gasoline engines. Active suspension can be passive, active or semi-active. In this paper, a development of semi-active suspension system using air fluid can be found. Here one marine system application is shown, that is S2DS, Smart Sleep Demonstration System. The objective was to develop a significant quiet environment improvement of about 10 decibel reduction in self-generated underwater torpedo noise using a compact and less expensive system. So, the solution came in the form of the development of a highly maneuverable underwater vehicle based on swimming techniques and anatomic structure of fish. Rediniatis and others developed and tested a biomimetic active hydrofoil that uses shape memory alloy for actuation. Controlled heating and cooling of shape memory alloy wires generate bidirectional rotation of the vertebrate, and this in turn changes the shape of the hydrofoil. There is growing use of smart materials for medical systems also. In medical systems, here the requirement is compactness, low weight, precise control has to be there, durability and repeatable operation is needed, and minimum invasiveness, that is also required for surgeries. Applications involve prosthetic devices such as artificial hands, knees and fingers, robotic eyes, artificial and sphincter and urethral valve, rehabilitation therapy, microrobots, telerobotic surgery, cancer therapy, microrobot swimming in blood vessels, eyeglass frames, orthopedic implants, orthodontic treatments, tissue fixators. There is a study by Dong and others. They developed smart variable resistance exercise machine using MR fluid dampers for rehabilitation of patients suffering from neuromuscular and orthopedic conditions. So, in an exercise equipment, generally the resistance offered is not so properly tuned. So, that is what they wanted to address here. So, when during the stretching, the maximum force, during the stretching at the beginning and at the end, the force is not maximum, generally the force is somewhat low and the maximum force is achieved somewhere in between. So, that is what they wanted to do in through this work. The strength offered by the resistance offered by this exercise equipment was tailored in such a way that when required it offers the maximum resistance. Minimally invasive surgery is quite popular now because of its several benefits, less difficulty to the patients. Now, small and compact surgical tools with viewing equipment attached to a long slender tube that is inserted into the body through a few small incisions about 5 to 10 millimeter are generally used for this. Now, the limitations of these tools are lack of dexterity and localization actuation of the surgical end effector and lack of haptic feedback to the surgeon. So, because of that, Rubio and others, they presented study of topology optimized design, microfabrication and static dynamic performance characterization of a electrothermomechanical micro gripper. The micro gripper design consisted of a symmetric monolithic metallic 2D structure. This consists of a complex combination of rigid links integrating both the actuation and gripping mechanisms. Now, finally, we will talk about energy harvesting applications. As was mentioned earlier, that energy harvesting wants to offer some smart solution to power requirement sensors and the electronic equipments associated. Here the motivation is that recent developments in low power and efficient microelectronics leads to interest in energy harvesting using smart materials. So, piezoelectric materials using the direct effect, the energy associated with mechanical vibration, part of it can be harvested. Now, there are several works in this area. For example, Sodano and others, they showed an aluminum plate attached to a piezoceramic plate could charge a 40 milliampere hour battery within a couple of hours. Now, when it comes to energy harvesting, there are a lot of observations. For example, in linear systems, the energy harvested is maximum when the frequency of oscillation is very close to the resonance frequency. So, the moment we are away from the resonance frequency, the harvesting efficiency is quite low. So, that is why in a nonlinear system we can do a more broadband energy harvesting. So, there are good amount of work in this area, and there has also been observation that in bistable systems the energy harvesting is even better. So, bistable systems can have small vibration within 1 potential well, I mean with respect to one stable configuration. There can be large amplitude vibration with respect to one stable configuration, and there can be large vibration where it shifts from one configuration to another configuration. So, when it does that, even more energy can be harvested. And also in especially in aeroelastic systems, if the system is prone to flutter, then instead of dissipating the extra energy, it can be meaningfully harvested for some special purpose. So, as was said that a flutter is a growing oscillation. So, the system the structural system starts taking energy from the aerodynamic system. So, instead of dissipating the energy by using properly designed energy harvester, the energy can be absorbed. So, the extra energy can be absorbed, with this stabilize the structure, as well as the absorbed energy can be useful for some meaningful purpose. So, there are endless possibilities. So, with this discussion on these diverse applications, we can see that there is endless possibility with smart materials and smart structures, but at the core of it lies proper material modeling and proper analysis. So, that is what this course is about. Now, we will gradually move into various smart materials and smart structures. From the next class, we will start discussing about piezoelectric materials. Now, so with this we finish this introduction. Thank you.